Vincenzo Kosor, first year of electrical engineering with experiences in flight autonomy and electronics, role mission coordinator. Mirko Borovac, fourth year of mechanical engineering with experience in construction processes, communications, role launch operator and parachute operator. Anita Borozan, our co-team lead. Josip Wolf, second year of software engineering with experience in image recognition programming, role, object detection, classification, localization. Duje Lukovic, third year of energy engineering with experience in communication, role, safety pilot, communications pre-check. Ivana Nikolic, first year of electrical engineering with experience in sensors and telemetry analysis, role, telemetry data overview. Hanna Malenica, first year of visual design communications. Marko Boljat, first year of software engineering with experience in mission planning, interop system, role, interoperability server operator. Matej Alinovic, first year of electrical engineering with experience in power systems and distribution, role, electrical engineer. Helena Knezic, first year of physics with experience in mission planning, role, air delivery operator. Tony Chobanov, first year of electrical engineering with experience in flight autonomy, obstacle avoidance, role, obstacle avoidance, autonomous flight controller. Mechanical subsystem, airframe manufacturing process. The fuselage and wings are manufactured using composite material technology so the weight will be kept at minimum while maintaining structural integrity. The wings and fuselage skin have two halves, each one made in its female mold. The materials used are glass fiber epoxy prepregs and thin Air-X foam for wings with Kevlar epoxy prepregs for the ventral fuselage. Curing was done by vacuum bagging in a pressurized autoclave. The wing internal structure has a classic airplane wing structure made from spars and ribs which are made from laser-cut plywood reinforced with carbon fiber and epoxy. The binding of the internal structure was done with a mixture of epoxy resin and microballoons used to connect the parts. The structures were then cured in a non-pressurized oven at low temperature. Winglets are 3D printed PLA filaments and the surface is grinded and primed for smoothness. Carbon fiber rods are used to connect the wings and fuselage. Catapult MXC-1. Our catapult is a pole cargo type with a frame made of aluminum profiles and a total of 18 pounds weight. The frame is separable and foldable with modules 3 feet long so it can be easily transported by air cargo or a car. It can launch up to 35 pounds UAS with maximum launch speed rated at 35 miles per hour. The Catapult MXC-1 with 10 feet length, main beam, sliding aircraft, holder and beam support, elastic cords are tensioned and the catapult is ready for launch. This image shows zone definitions for the pole cargo type catapult and crowd positions in the catapult zone. The catapult beam must be prepared for operation by the catapult team, chief and deputy, following these steps. Preparation of assembly area, collecting parts and tools, assembling the catapult, setting safety locks and safety zones, tensioning elastic cords one at a time, setting up the aircraft, checking safety locks again, and submission of the catapult to the pilot team. After completing these before mentioned steps, the pilot crowd, pilot and deputy pilot, should launch the aircraft. Deputy pilot releases the locks, pilot gives launch permission, and deputy pilot releases the trigger. When the catapult is in attention state, security locks make it safe for use. MXC-1 has two security blocks. The blocks are released one after the other and the release is made with the foot pedal. Catapult team visually check the state of elastic cords after every launch operation and before the next launch. Electrical subsystem. Propulsion. For propulsion, the VX-3 uses a single Scorpion V2 brushless motor combined with an Aeronaut 12x8-inch propeller and a Scorpion Tribunus electronic speed controller. Propulsion is powered through a parallel combination of a 4-cell MaxAMS lithium polymer battery for a total flight time of 90 minutes at cruising speed. Wires that connects the ESC and motor are 12 gauge which can sustain 200 amps and 6500 degrees Fahrenheit. Power supply block converts input voltage of 14.8 volts to 5 volts 3 amps for onboard electronics and 24 volts half amp for communication equipment. Power cables are separated from data cables and antenna cables to prevent interference. Software subsystem, obstacle avoidance. A-star obstacle avoidance is a matrix-based algorithm that selects the fastest route from start to finish. Since it is matrix-based, the UAS has 8 possible ways to choose from in any given time. The algorithm calculates the shortest path via formula F equals G plus H, where the G cost is the horizontal shift and the H cost is the vertical shift. In traveling from the starting point, the algorithm is creating a variety of possible paths, and when the goal is reached, the path with the lowest F value is chosen, meanwhile avoiding any possible obstacles. Interoperability system works as a server-client application that takes care of necessary data for a successful mission. The system uses HTTP API calls to a server for making requests. Object detection, classification, and localization. After conducting a number of test flights using the GoPro camera, the data collected showed a low percentage of recognized targets due to the rolling shutter. Upgrading to the Sony Alpha 6300, we received satisfying results. Further improvements were made by implementing the autofocus and optical stabilization options while recording. The average resolution of all objects depends on the height of the UAV operates on, so after lowering its operational height, an improvement of 30% for image quality was made. Our custom-made algorithm ensures no falsely recognized images get forwarded to the interop server. Detection and classification. An improvement rate of 47% was achieved in detecting targets because of better training data for our custom AIR. Current success rate exceeds 80% with a 20% failure due to bad weather and vibrations caused by the UAV's propulsion system. Custom-written software used for detection and classification allows for fully autonomous image recognition as well. Air delivery. Our air delivery system was designed based on preliminary calculations and testing, such as parachute rate drop and payload trajectory. After a variety of conducted simulations in MATLAB, we found a suitable algorithm for precise timing of airdrop triggers. For the release mechanism, a servo was used to secure the UGV to the fuselage. While attaching the payload, we succeeded in maintaining the center of mass before and after the drop. Unmanned ground vehicle. UGV's core function is autonomous navigation, which directs it to the selected area. Navigation is achieved with a custom-made circuit board based on Atmel 32U4 microcontroller and electronic components, MOSFETs and resistors. Autopilot will communicate with a wireless module operating at 433 MHz to provide telemetry to ground control station. Ground control station is also able to manually shut down the UGV in case of emergency. Commercial ESCs were less suitable as they have insufficient output voltage and additional weight. UGV is powered by Turnigy lithium polymer battery, which is light enough and has enough capacity to power the motors for the planned mission duration. For the parachute, the team decided to use Iris 36-inch light parachute from the Frida chutes for its lightweight and compact packing volume. Parachute is capable of 4 pounds weight at 15 feet per second sync rate. The parachute is retracted with continuous rotation servo motor connected to the customized roller. Telemetry. There are two communication channels between our UAS and ground control station. 433 MHz DragonLink V3 used as a telemetry link between the mission planner and the flight controller and as an RC control link for the safety pilot. To achieve better photo or video stream, we use dual band 2.4 or 5.8 GHz Ubiquiti AirMax link, which consists of the rocket base station and a bullet transceiver in the UAS. Also, a point-to-point wireless link established by Ubiquiti Rocket and Bullet AC pair is used for providing main data path between the UAS and the GCS. 868 MHz telemetry link established by RFD 868 pair for providing a backup telemetry link. Autonomous flight. Autonomous flight starts with route planning, mission objectives, checking weather forecast, testing functionality of aircraft, testing functionality of catapult, testing functionality of ground control station, testing functionality of support equipment. It consists of auto takeoff, catapult or bungee cord, mission, waypoint path, search grid, payload delivery, and auto landing, belly landing or parachute landing. Configuring the autopilot to accomplish given task is very airframe dependent. Necessary parameters for UAS capabilities are minimum speed, cruise speed, turn radius, pitch angle when climbing at full throttle, pitch angle in horizontal flight at cruise throttle, maximum flight time. This information tells us how hard the autopilot can push an aircraft without losing control over it. Autopilot uses PID controller for controlling attitudes such as roll, pitch and yaw. We can manually set these parameters or we can implement auto-tune for specific results. When the flight controller is properly tuned, we can be certain that the aircraft will fly nominally inside its boundaries. It is imperative for the success of the mission to coordinate all these systems so we don't have a conflict between what we want and what is possible. Parachute system. Our parachute system consists of a parachute, storage box, lid, and suspension lines connecting the assembly to the fuselage. The storage box is a part of the UAS's skin and it stores the parachute as well as the suspension lines. The lid that closes the box also works as the pilot chute that pulls the suspension lines and the main chute once the system is activated. The system is activated by pulling the pin from the lock. The lid is pushed by the spring into the airflow, which then freely pulls the lid further from the plane. The lid then pulls the brake, suspension lines, and the chute, which leads towards the chute deployment. Just before the maneuver, engine is shut off and the plane nosedives so the airflow can pick up the lid. In the first run, a 1.5 gallon bottle was dropped from 60 feet. The parachute was deployed under 2 seconds, descending at the average speed of 20 feet per second. The descending velocity was considered satisfying since the shape of the bottle isn't very aerodynamically pleasing. In the second run, the system was tested on the plane manually, and the plane descended at the average velocity of 16 feet per second, gently landing on the belly. Both tests were conducted in monitored conditions and had successfully passed set criteria. Mission testing, detailed mission description. Flow Design team is attempting all mission tasks this year and is confident about the VX3 performance level. For estimation of scoring at the mission demonstration, we attempted 7 full mission tests, in addition to the 17 hardware and software test flights, with 66% of the time spent in an autonomous flight and 34% in manual. Prior to flying the UAS, team used mock runs with ground runs, which consisted of all aspects of the mission apart from the demonstration. This helped to eliminate any inconsistency in the mission flow procedure. First up is the timeline aspect. Team consistently tested if the UAS can be set up and ready to fly within 10 minutes with time to spare. Prerequisites for that result require proper planning up to 3 days ahead of the mission, starting with mission objectives and personnel pre-flight briefing. Next, weather reports are checked to ensure safe operation. Pre-flight checklists are run to ensure all tools are accounted for, batteries charged, UAS setup, and safety aspects are met. On the flight day, checklists are reconfirmed. Mission time was on average completed in 15 minutes, with all elements of the mission included, significantly below the cutoff margin of 40 minutes. This leaves enough time to repeat failed portions or retake elements to gain better scoring. The team will attempt to avoid taking timeouts and only defer in case of a major malfunction. For autonomous navigation, a goal of 3 minutes of auto navigation was achieved on 90% of flight. On flights which lasted beyond the initial stage of takeoff and climb out, 66% of flights achieved full autonomy. Waypoint accuracy consists of flying a predetermined pattern with the aim of passing the waypoint as precisely as possible. Average accuracy was 100% within 100 feet. Obstacle avoidance was tested again with interop feeding a flight plan that had randomly spaced no-fly zones. Several levels of sparse to saturated no-fly zone distribution was used, and the UAS achieved 75% obstacle avoidance success on average, with the expected level of OA density for the demonstration having a success of 98% and 100% reliability on not breaching the boundary line. Imaging performance consists of accurately detecting, classifying, and localizing the object of interest. Detecting is achieved with the Sony Alpha 6300 camera, coupled to the onboard computer which sends snapshot every half second to the ground via 5.8 GHz link down to the GCS. Areas where the team expects problems to occur is the non-existence of gimbal, which would allow for better localization and off-axis targeting, for which we need to roll the airframe. After processing the image, parameters of orientation, color, shape, character, and geolocation are transmitted via interop. In total, our mission setup managed to detect 10 out of 12 targets tested, with 80% accuracy in all parameters. Finally, the last mission parameter is the airdrop. A simple release mechanism is tied into the flight controller. Custom algorithm calculates the optimal drop point, and once a green light is given from the judges, the UAS executes a proper airdrop pass. By releasing the UGV, a parachute is also released with the same action. The team has tested the airdrop requirement for 7 times and achieved a drop within 75 feet on 70% of drops. With that, the mission is concluded, and the UAS returns to home location, pitches up, releases a parachute, and glides to land. Teardown consists of packing up the GCS and collecting the UAS from landing position, which is also achievable within a loaded 10 minutes. After conducting 24 test flights while constantly improving the flight line procedure, the team is fairly confident about its operational excellence.